Hi, Assalamualaikum. For this session, we are going to discuss tutorial 12. For the additional question, a cesium surface is illuminated with light of wavelength 450 nanometer. The work function of the metal is 2.58 electron volt. Then calculate A, kinetic energy maximum of photoelectrons, B, the cut-off wavelength of the cesium, C, the maximum speed of the photoelectrons. So let's look at the solution. This is the metal, the cesium. The cesium has the work function of 2.58 electron volt. Work function is the minimum energy for the electron to be ejected from the metal. Okay, this is the incoming light incident on the surface of the metal. The light has a wavelength of 450 nanometer. That gives you the energy of the photon. Okay, you can calculate the energy from this equation. Energy of photon equals to Hf, Planck constant, times the frequency, or the Planck constant times the speed of light divided by the wavelength. So this is the electron on the surface of the metal, and then this is the ejected electron with certain velocity if the energy of the photon is greater than the work function. So we are going to find the velocity, the speed of the ejected electrons later. Okay, and then the electron also has a mass, because electron is a particle, so it has a mass. So for A, you need to calculate for the kinetic energy. Okay, for the kinetic energy of the electron, you can calculate from this equation. Kinetic energy equals to half the mass of electron times with the speed of the ejected electrons. But now you need to calculate the kinetic energy by using the energy of the photon and the work function of the metal, in this case cesium. So energy of photon minus with the work function, hc over lambda minus the work function of the cesium. So h is the Planck constant, 6.63 times 10 to the power of 34 times with the speed of light, 3 times 10 to the power of 8 over the wavelength of the light, which is 450 times 10 to the power of negative 9 in the region of nanometer, minus with 2.58 electron volt. Okay, you need to remember the SI unit for energy is in joule. You need to convert the electron volt to the joule. So the equivalence is 1 electron volt equals to 1.602 times 10 to the power of negative 19 joule. So you can cancel the electron volt. So the answer is 2.92 times 10 to the power of negative 20 joule. So I have made the note here. The SI unit for energy is joule. So it is safe to convert everything to joule before you do the calculation. Okay, and then question B, you need to calculate for the cut-off wavelength. Okay, cut-off wavelength coming from the work function equals to hc over cut-off wavelength. Then you need to rearrange the equation as lambda c equals to hc over the work function. Okay, this is the value of the work function given in the equation in the question. So equals to time constant 6.63 times 10 to the power of negative 34. Okay, times with the speed of light 3 times 10 to the power of 8 meter per second actually, over the work function in joule. Okay, you need to convert the electron volt to the joule using this equivalency. Okay, so that you can cancel the electron volt. So it is actually better for you to write the symbol rather than the value there. And then the value for the cutoff frequency is the cutoff lambda, actually the cutoff wavelength is 4.81 times 10 to the power of negative 7 meters. Okay, C, you need to calculate for velocity actually. Okay, that's the maximum kinetic energy. Okay, kinetic energy maximum equals to half ME. ME is actually the mass of the electron. V max is actually the speed of the ejected electron. Okay, that's correct. You need to find the velocity or the speed of the ejected electrons. So the maximum velocity or speed is 2 kinetic energy maximum divided by mass of electron, and then the answer is 2.51 times 10 to the power of 5 meter per second. Okay, don't forget to write the unit meter per second. So the K max, the value of the maximum kinetic energy, you can get from question A. Okay, and then the value for mass of electron you can get from your textbook or from the cover of your calculator. Okay, I hope you understand. See you.